Hello everybody, welcome to the next video in the series of Physics at Home. This is an apparatus you don't really see at home. This is called as a microwave apparatus. The word microwave comes from the range in electromagnetic spectrum in which the wavelength of the light matches that microwave region or that part of the spectrum. This experiment, this apparatus has two parts. There is a transmitter and there is a receiver. Okay. Now, the transmitter here, inside of which there is a vertical pin. Inside of this pin, there are charged particles moving up and down. They're giving out light. The light that comes out is polarized. Polarized means that the electric field of that light is vertically aligned. Unpolarized light means that the electric field is randomly aligned. Okay? So, if the light is coming out and it is vertically polarized, then there is a receiver here which will receive that light. Okay? On the top of the receiver, you see a display. When the light is captured, it's converted into current and that current is measured. Okay. So let me turn this transmitter on. As you see on the display here, the needle was 0, now it's showing about 0.9 milliamps. So the light is sent out, it's captured by the receiver, converted to current. Okay. Now, the idea of today's experiment is to explore the vector nature of electric field. Electric field has direction. Okay. Now, on the back of the receiver, you're gonna see, there is a scale here, right? And it's like a protractor, so there are markings on it going 0 to 360 degrees. Same scale also exists on the back of the transmitter, which is useful to figure out or to record that if you turn it by a certain amount, what happens to the amount of light that is captured, which is directly displayed as the current. So let me turn this transmitter now. Now watch the needle. Slowly the current is dropping, meaning the amount of light that is absorbed is dropping. Drop all the way to 0. 0 current would mean no light has been received by the receiver. Now even though the light has been sent out, nothing is blocking here right now. The reason why there is no light received by the receiver is because the receiver also has a pin which is vertical. Earlier, when light was being received, the transmitter and receiver earlier were parallel to each other. But we turned it, and now the transmitter is sending out light which has electric field horizontal, and the receiver antenna is vertical. So because there's 90 degrees to each other, no light has been absorbed. If I go the other side, same thing. So it doesn't matter, if I turn it, over here or turn, positive 90 or negative 90. As long as the transmitter is perpendicular to the receiver, no light will be absorbed. So in the first part of the experiment, what I'm going to do is I'm going to record the current as a function of degrees of turn. And I'm going to go from negative 90 to 0 to positive 90. And as we saw that at 0 degrees, 0 meaning, the relative angle between the transmitter and the receiver. When it is 0, meaning when they are parallel, we're going to see maximum current. For any other angle, it drops, right? So it's going to be like a cosine curve. Okay, that will be the part 1 of the experiment. But the part 2 of the experiment involves this polarizer. Okay. Right now, we know that the transmitter is perpendicular to the receiver, so no light has been absorbed. And if I stick my hand, nothing doesn't matter because already nothing has been absorbed, right? Now watch what happens. If I stick this polarizer in between, watch the needle. Well, now I'm getting some light absorbed, right? So some of the light is received here now. So what is this polarizer doing? Well, to understand what this polarizer is doing, first we need to do another set of experiment here. Alright, so let's go back to the 0-degree position where both of the transmitter and receiver are parallel to each other. And let's take this polarizer with its slots vertical. Okay. So we are saying that right now, the polarized light has electric field vertical, so light is coming this way. And if I stick this polarizer in, then the light should be able to pass through, right? Because the slots are vertical. What's the needle? It's almost zero. There's a point where we saw it as 0, right? Well, what is this one doing? Well, this here gives us an insight as how the receiver works. The receiver is also a metallic pin, and as long as the pin is vertical, and also the transmitter is vertical, all of the light gets absorbed by the polarizer. Think about it now. That means that if I turn this horizontal, right, meaning if I have my receiver perpendicular to the transmitter, none of the light was recorded, correct? Meaning all the light passes through, right? So technically, when I stick this in, okay, none of the lights should get absorbed. Okay? So see it here. See, you got almost the same, or actually we get a little bit higher, but anyway. So we get almost all of the light passing through. The polarizer is not affecting the amount of light that is passing through. So if the electric field is perpendicular to the polarizer, then the polarizer doesn't change that electric field. But if the polarizer, the slots, if they are parallel to the electric field, then it captures the light. Okay? So the second part of the experiment is sticking the polarizer at 45 degrees. And right now, we don't have 0.9, but slightly lower than that, right? So there is some light that is absorbed by the polarizer, and the rest of the light passes through and received by the receiver. Now, we are saying that now the transmitter is vertical, correct? So electric field is vertical. Yeah. Now watch what happens. What's the needle again? Now I'm going to turn the transmitter in such a way that it becomes perpendicular to the slots here. Okay. So if I turn it, see, now I'm increasing, correct? Now the polarizer is not absorbing any light. All of the light, because it hits it perpendicular, it passes through, and then it hits the needle there. Okay. More so, if I turn it the other way and make it parallel to the slots, see, nearly all of the light is now absorbed. So the polarizer is now blocking the light. Okay. So in the second part of the experiment, what I'm going to do is stick this polarizer at about roughly 45 degrees and then do the same measurements. But I go from -90 to 0 to +90. And you're going to see what happens to the plot compared to when there was no sleeve, or no sieve, or no polarizer. Think about it again. The question is that right now the transmitter and the receiver are perpendicular to each other. So no light is received by the receiver. But as soon as I stick this polarizer in between, what it is doing, it is changing the direction of the electric field. So until the electric field hits the polarizer, it is horizontal. But after it hits the polarizer here, the electric field changes the direction. So instead of horizontal here, now it gets perpendicular to these slots, and then it hits the receiver such that the transmitter is sort of like in that direction, not horizontal but turned around. Okay, so in the second part of the experiment, we're gonna look at how the vector nature of the electric field comes into the play.
In this plot here, we see the current as a function of the angle of the transmitter. Maximum current was recorded when the transmitter was vertical, and that vertical transmitter meant the angle between transmitter and receiver was 0 degrees. If we turn the transmitter either ways, the current dropped off, correct? To understand this, we're gonna just briefly mention here what is a Malus's law, which is I equals to max times cosine square theta, and I represents intensity. So this law applies to a receiver, which captures light, and then the intensity of light that is captured is directly proportional to the square of the amplitude or the maximum of the electric field that that light had, because of which there is a square here. Now, loosely speaking, for our experiment, the intensity in the Malus's law, is we're gonna relate it to the current that we're measuring. Okay. When transmitter is at 0 degrees, then the angle between transmitter and receiver is 0 degree. What it means is the light that comes out from the transmitter has electric field vertically polarized, and that electric field, when it hits the receiver, then the angle between the electric field and receiver is 0 degrees. So if you plug it into this cosine theta, cosine 0 is 1, square it becomes 1. So the current that the receiver records is the maximum that it can. Okay. If you tilt the transmitter by 30 degrees clockwise, that is in physics is negative 30, then the electric field turns with it. Now this electric field that comes out from the transmitter and hits the receiver is now 30 degrees clockwise turned with respect to the receiver. So if you plug it into cosine theta and then square it, it's about 0.75. So not all of the light gets absorbed. A part of it gets absorbed, a part of it just passes through. And how much, or is there a way to visualize it? Well, indeed. We're talking about vector nature of electric field. So if we remember, vectors have components that we can break them down into. Okay. Here we can break this red arrow, this electric field, into two components. A component which is parallel to the receiver and a component perpendicular to the receiver. Yeah. As you can see, there is a 90-degree angle at every point here. So this electric field can be considered to be a combination of vertical and horizontal. The vertical field is, according to Malus's law now, has an intensity, or it's about 0.75 of the maximum that occurs in, and that is absorbed. The horizontal passes through. So if you look at it here, at about at 0 degree we have about 0.9, and then at about 30 degree or so angle we get about 75% of that. Yeah, so that's what is going on. If you turn the transmitter to 90 degrees or negative 90 degrees, then the electric field is now horizontal, and now the angle between electric field and the receiver is 90 degrees, and cosine 90 is 0. So the current that is recorded is now 0. What we saw that If there is no polarizer between the transmitter and the receiver, then at negative 90 or positive 90, there was no current recorded. But as soon as we stuck a polarizer in between, then immediately there was some current recorded, correct? At these negative and positive 90s. Now let's see what is going on. Now to understand what's happening at these two extreme positions, we need to first look at, why the peak was at 0 and now it has shifted to 45 degrees. And then, the minimum here is no longer at negative or positive 90, but at negative 45 degrees. So still there is a peak to valley, the angle is about 90 degrees. That still is there, but the peak has shifted by about 45 degrees. So what exactly is this polarizer doing? So here is one of the orientations, that the transmitter is at 45 degrees, positive 45. Polarizer is at negative 45 degrees. So if you turn the transmitter in this direction, we know the electric field turns with it, correct? So this electric field, when it hits the polarizer, then now the electric field is perpendicular to the polarizer, correct? And what we saw in this situation, when the electric field hits the receiver, if it is perpendicular, then receiver does not absorb any light. Yeah. Same here, polarizer does not absorb this electric field or this light, so it passes through. And when it hits the receiver, this is similar to this situation, except now the angle is different. Here the angle is 45 degrees, so if you plug in cosine 45, square it, it's about 50%. So the current is now dropped to about half of what it could have been. If you turn the transmitter and make it parallel to the polarizer, now the electric field aligns with the polarizer, and just like in this case, polarizer now absorbs all of that light. So theoretically, nothing should pass through. But we do see that at negative 45 degrees here, we do see some current, and that has got to do with the plane of the polarizer not being exactly parallel to the plane of the electric field. But nevertheless, these two positions now tell us that the negative or minimum of the current will happen at negative 45 degrees, and maximum current will be recorded at positive 45 degrees, correct? So that's why the peak has shifted. Now we come to the final part here, where to understand what's going on at negative and positive 90 degrees. When we turn the transmitter horizontal, so the electric field is horizontal, and now it hits the polarizer at 45 degrees, correct? So polarizer is about 45 degrees to the electric field. And just like we break the electric field into parallel and perpendicular components, this electric field we can break into parallel and perpendicular components. The parallel component gets absorbed. The perpendicular component passes through. Angle is 45, so we get 0.5 of intensity, or current, that is or the electric field that is passing through. And this one, now think about it, without the polarizer, electric field remained horizontal when it hit the receiver. With the polarizer, electric field is now turned from horizontal to this angle here, right? This angle which is perpendicular to the polarizer angle. And when this electric field hits the receiver, now we can break this electric field into its vertical and horizontal, or parallel and perpendicular components. So the receiver is not completely blind to it. Some of the electric field gets absorbed, some doesn't. So now, even though this is negative 90 or positive 90, the other way, then we know that the receiver would still be able to absorb or sense light. that after passing through this polarizer, the electric field gets turned. Okay, so here we hopefully are able to lay it out how the electric field's vector nature comes into the play. Okay, so last week we saw vector nature of the magnetic field. Today we saw vector nature of the electric field. Two together, they are part of the same exact concept, which is electromagnetism or light, so to speak. And that's exactly what we're going to do in the next week's lab. We are going to do some fun experiment with light and lenses. Have a good one.